Now, the algebra involving the calculation of impedance and reflection coefficients along transmission lines is a bit involved. It involves complex numbers. It's not straightforward to understand how these parameters evolve along the transmission line. And for this reason, Philip Smith, which was working in Bell Labs in the 1939, invented the Smith chart, which is just a polar representation of the reflection coefficient gamma, but it's very, very practical and to use not only for calculation, but for understand or to get a physical insight of what's going on inside the transmission line when you move back and forth, if you have reflections, if you have to match a load which is not coincident with the impedance characteristic of your generator or transmission line, what do you have to do? You can actually use this tool, this graphical representation tool, to understand and to calculate solutions in these cases. So let's take a look to this Smith chart and how to use it to solve different problems in transmission lines. Well, the Smith chart is a polar representation, so it has a circular shape. You have many circles inside. These circles are representing impedance, real and imaginary part of impedance. And we have here, for example, the left part of the Smith chart, if you use this chart to represent impedance, is a low impedance condition. So, for example, this point here, this particular point, is a short circuit. This is Z equal to 0 in real part, and the imaginary part is equal to 0 as well. So this is this point. If we take a look to the other side of the horizontal axis of the chart, we go to this point. This is a high impedance point. So this will be at the very end of this line. That would be an open circuit where the impedance is infinite here. And we have also the periphery of the chart is labeled with wavelength units, and you can move along the transmission line in two senses, or either towards your load, and then you have to move radially following this sense here, and if you move clockwise, this represents moving towards the generator of your solutions, of your impedance or your reflection coefficients along the transmission line. Also, the radius from the center represents important parameters in the transmission line, in particular standing wave ratio that we have seen before when we have a reflection coefficients, and also losses due to mismatch if we have a reflection at the end of the line, and so forth. So let's make an example. Let's use the Smith chart to represent an impedance. So let's, for example, assume we have a transmission line, which is ended by an impedance which is different from the characteristic impedance of the transmission line. 50 ohm is a very typical parameter, by the way, because this is the reference impedance for most radio frequency applications, wireless applications. That's 50 ohm is a very important reference in practice. So let's assume a 50 ohm line is terminated by an impedance which is different, 100 plus 150 ohm. This imaginary part represents, for example, some inductive parameter component of this load. Now, we want to represent this impedance in the Smith chart. The first thing we have to do is to normalize the impedance. So if the reference, our transmission line reference is 50 ohm, we normalize the load impedance with respect to this 50 ohm parameter, and we get this new impedance which is normalized. Now, we have to represent this point in the Smith chart. How to do that? Well, we have to understand, we have two families of circles. The circles that actually are centered along the horizontal axis of the chart. These circles here are representing real part of the impedance. On the other side, the circles which are tangent to the horizontal axis, these represent imaginary parts. So now, we have this 2 ohms real part corresponds to this circle. This is the circle of 2 ohms. Now we have also an imaginary contribution, this corresponds to this circle here. Now, our complex impedance will be just the intersection of these two circles, or what is the same, this point here. And now, from the center of the chart, the radius of this point is actually the modulus of the reflection coefficient gamma. And this phi here parameter is the phase of the reflection coefficient. So the Smith chart gives us directly, or relates directly, reflection coefficients and impedance, real and imaginary parts. And okay, if we take a look to this modulus, and then we use the radial axis of the Smith chart, we can actually interpret this modulus in other parameters. For example, reflection coefficient, this is which is 0.75 in this case. We can actually take a look to the phase, which is 26 degrees, is this angle. But now, this is related to the standing wave ratio. We have a reflection here, of course. The termination is not coincident to the characteristic impedance of the line. So we have a reflection, and this is producing a standard wave situation with a standard wave ratio parameter, which is 7, or if you express it in dBs, 17. We have made this example with impedance. What happens if you want to work for some reason in admittance, which is it is just the inverse of the impedance parameter? Well, it happens that the Smith chart, due to their properties, can be used altogether for impedance or admittance. You know, if you have, for example, this situation, an impedance which is this parameter, once it's normalized, is this point, it is represented here, and now you want to find out what will be the admittance. You have two options. You take a calculator, a complex number calculator, and you find what is the inverse of this number, or you can just use the Smith chart. You take this point, you rotate the phase 180 degrees. This is the phase change of a quarter lambda transformer. Remember that a quarter lambda transformer gets, if you work with normalized impedance, it obtains directly the inverse value of your impedance. It's an impedance inverter. So, and that's what we want to obtain. So the impedance inversion normalized in normalized expressions, it provides you the admittance parameter. So you can use the Smith chart. You just change your phase, you go to the opposite point here, and you get right away what is your admittance at this point. You denormalize your admittance, and you get in Siemens your value. Also possible usage of the Smith chart. Another usage of Smith chart is, okay, let's calculate the input impedance of this situation here. We have a transmission line with some parameter, characteristic parameter. It is terminated with a different impedance, and we want to know what is the input impedance here. Again, we have two options. We can take our calculators, we have expressions, or MATLAB, and we can make a numerical computation of this, or we can just take the Smith chart and calculate it graphically. What happens here? Well, we have a load, this impedance here. Once it's normalized, we get this value. We represent this value, real part. The imaginary part is here. So the impedance is represented by this point. This is the reflection coefficient at this point, at the end of the line. Now, we are interested to calculate not here at the end, but at the input of the line. And we have a line of certain length, for example, almost half lambda, 0.45 lambda in length. How can we calculate that? Well, we know that the reflection coefficient, actually, it is in a low loss situation, it preserves the amplitude and only changes its phase. So the reflection coefficient here at the input can be readily calculated just by moving towards the generator, because we are here in the load. Now we are moving towards the generator, so we rotate here clockwise along the Smith chart, and we get this point here, which is actually the reflection coefficient at this point. Only the phase has changed, and we can actually transform this reflection coefficient, amplitude and phase, into a new impedance here, and that's the impedance at this point, the input impedance of the transmission line. Of course, this is normalized. We denormalize the value, multiplying by Z0, and we get the complex impedance here at the input. So again, this is actually can be used as a calculator, a complex calculator, but also it provides, and that's very interesting for this reason, it provides some insight of the physical evolution of the signals along the transmission line. The reflection coefficient only changes phase, and this ends up with a different impedance compared to the one we have at the output. So an impedance here at the output is seen as a very different impedance here at the input, depending on the length of the transmission line and its characteristic impedance.